I'm not trying to solve the many-body problem, because that's a hard problem to solve. But I am interested in describing electronic properties, and particularly my specific interest is in excited state properties of extended system. And when I say extended system, I'm talking about systems that contain, say, on the order of 10 to the 5 electrons or more. It could be 10 to the 6, it doesn't really matter. And that you do need an atomistic description of the physics or whatever you want to describe that comes out of that problem. Because of length scales, and mainly because of length scales. And so any excited state calculation, you must all know that, has to start from a ground state calculation. And we've developed a lot of stochastic techniques within the realm of the methods that we use to describe excited states in semiconductors to reduce the scaling of excited state. And then we ran into a problem by which the ground state calculation was the bottleneck, not the excited state calculation. And so this talk is going to focus on the developments that we have taken to lower the scaling of ground state calculations that we can then use as our starting point to do excited state calculations, which I'm not going to talk about whatsoever. And then I want to apologize also because some of the things that I'm going to cover, some of you probably have heard me talk or maybe have heard my collaborators talk about the subject. And so I am going to review to some extent what we've done early on with stochastic DFT, just because it's the simplest algorithm, and I think you can just get a sense of what we're doing from the simplest approach. And then I'll show you how we fight the same war that I've heard this morning, which is to reduce the statistical fluctuations and the errors. And we've developed various different schemes to do that within the stochastic DFT formalism. And then finally, I'm going to show you a cool application to warm dense matter, which is another challenging system for DFT, particularly at high temperatures where you need to solve for all the Kohn-Sham eigenstates. And that becomes a big bottleneck if you want to converge calculations on warm dense matter. So I'll show you some applications with stochastic DFT and the scaling, of course. And then finally, I already mentioned my collaborators, Danny and his group and Rui and his group. And most of the work that I'm going to describe here was done by Ming Chen, who was a student of Mark. And thank you, Mark, for sending him to me. And he spent a few years in my lab and now is an assistant professor at Purdue. And so the first thing I want to tell you is about what I call the stochastic orbitals and stochastic trace formula. So unlike quantum Monte Carlo, we work with the notion of stochastic orbitals. We recently wrote a review. We call those stochastic vectors. Every time we change the name a little bit, but it's the same meaning. And the idea is very simple. I'm going to use a real space representation to represent my wave function. It's just easier for me to think about it this way. But anything I'm going to say, of course, works on any basis set. But all the examples will be from real space grid methods. And so a random orbital represented on my three-dimensional grid, in this case I'm showing a two-dimensional projection, is just an orbital where on each grid point it has a random phase. Now, often we don't do it with a random phase because when we work with complex numbers, it takes a little bit more memory and a little bit more other things. And so a simplification of this is that you can just use plus and minus one randomly, equally distributed on each grid point. So if I think of a one-dimensional wave function, sorry for those who are in Zoom, but I think most of them went to sleep in Europe, is I just take a random value, either 1 or -1 randomly. And this is a random orbital. That's how it looks like. And so, of course, it's a superposition of all eigenstates of your Hamiltonian. And then, interestingly, you can prove, and we haven't done any of this. This is, of course, done by mathematicians. It's hard for me to find who. If you guys know who is actually were the first to think about this, please let me know. But the idea is that you can represent the unit operator by taking an average over these ket bras, over these projections on each of the normal of the stochastic orbital. So in other words, the unit operator can be represented exactly as an infinite average over such stochastic realizations. And of course, the advantage of this approach would be that we're going to use a finite set to represent the unit operator, which will introduce an error in how we represent the unit operators, and then we'll have statistical error. We might have a bias depending on what we are trying to describe, but that's the basic idea. And so if you can represent the unit operator this way, you can also perform traces over any matrix, and a trace over any matrix within the stochastic formulation is just take the matrix element that you're interested in within the stochastic basis and recalculate that average as many times as you can to get a small statistical error, and that would give you an estimate to the expectation value of A. And so two basic ideas that are very simple, and what we're going to do is what we basically did is just put them together for a density functional calculation within the Kohn-Sham formalism, but we don't have Kohn-Sham orbitals, and this is what I'm going to show you next. Oh, before I do that, just to show you how it works on a simple system. So let's say I'm interested in calculating the density of states, and the density of states is just given as a trace over the imaginary part of the Green's function. And so I'm going to represent this Dirac delta function by a narrow Gaussian with eta. And the idea is that to calculate the density of states at any energy, I'd have to calculate this trace. So what we typically do is we diagonalize the Hamiltonian, get the eigenstates, and then we can obtain a function of the operator of the Hamiltonian that way, and just sum over. With the eigenstates, we can just calculate easily the density of states, but then this is an n-cubed operation, particularly for me when I'm interested maybe in sparse matrices, but just too many states, the orthogonalization and the linear dependencies make it an n-cube operation regardless if the matrix is sparse. And so with the stochastic trace formula, we just split this delta function. We just take the square root on both sides to write it in a symmetric way. And then we define what I call a filtered stochastic orbital. We apply this Gaussian function on a random orbital by expanding it in some series. In this particular case, we often would use a Chebyshev series or a Newton interpolation series. And the reason we do that is because we can just use one. There's a recursion relation by which we use one series of NC applications of the Hamiltonian and generate the density of states at all energies with one series. And so the idea is that to calculate the density of states, again, we do it with a trace. In this particular case, the trace involves an exponential of a function of our operator by which we expand in the Taylor series, and then we can just calculate the trace using the stochastic formula. And this is how it looks like. The final result, we just write the density of states in terms of what we call the residues and the Chebyshev expansion and the Chebyshev coefficients. And this is how it looks like when I just used 10 stochastic orbitals for systems. This is cadmium selenide nanocrystals going up to 2,000 cadmium selenide atoms together, which is about, I'd say, on the order of 10,000 electrons, valence electrons, of course. And I'm showing you here the density of states. It's normalized in a very weird way because the gap changes and the system size changes and the density of states increases with the volume. So I've rescaled everything just to show you the volume scaling. But the key that I want you to get from this is that with just 10 stochastic orbitals using 10 Chebyshev expansions, I get a pretty good estimate of the density of states, which is quite remarkable for a system that, if you think about it, contains 10,000 electrons for the biggest one, only in this region of the valence states. Now, it turns out that this stochastic idea has been proposed before us to calculate the density of states, and it's known in the community as the moment method. It's exactly the same as this, but this is just a different way of deriving it or looking at it and justifying it. And the method, the moment method has been very useful in getting linear scaling calculations of densities of states. And so the next thing, of course, that hasn't been done before we came to think about it is to implement this idea of using stochastic orbitals in density functional theory. And in density functional theory, when we have in Kohn-Sham formulation, we have a Kohn-Sham Hamiltonian, and we often would write the density as a sum over the orbital, the Kohn-Sham orbital densities, psi squares. And the factor of 2 here is I don't have spins. It's just to account for spin degeneracy. And this is the traditional way. So you need to find the Kohn-Sham eigenstates, and that's an n-cube operation. And when you have 10 to the 6 electrons with the size of grid of basis sets that we use, which is much bigger, and it's a converged basis set, it's just impossible to do. Unless you have a super duper computer, which is dedicated to your lab, which can give you 50,000 nodes a day to do a calculation like that. And we don't have that regularly available. We can do a calculation like this once a year. But if we want to do something routinely on a cluster, we need something better. And so the density, which is the density of the electron, the three-dimensional density of the electron, which is the main quantity in Kohn-Sham theory, it can be written as a trace over the projection operator theta projected over the occupied states, and then a trace over RR, which is just a density operator. And so if you use this expression to write down the trace, and you can prove to yourself that this expression right here is equivalent to this expression if you do the trace in the eigenstates of the Kohn-Sham Hamiltonian, but we don't have to do that in the eigenstates of the Kohn-Sham Hamiltonian. We're just going to use, where did that happen? We're just going to use a stochastic representation of the trace, and in the stochastic representation of the trace, we just have to apply this projection operator onto the occupied space, apply it onto a random function, do it on the other side, so we don't have to do it twice, and then just repeat this multiple times. So for notation, I've used the projection of the stochastic orbital onto the occupied space, and theta here is going to be a Fermi-Dirac distribution, and with a finite temperature. I'm going to call that a projected stochastic orbital, and we labeled it here by, is this theta or chi? I'm always confused. And then we're going to use a Chebyshev expansion, just like before, to calculate this projection operator onto the occupied space. And in Kohn-Sham formulation, whether you use different basis sets, you can make sure that the Hamiltonian is sparse. And that's a key in all these stochastic applications. So the overall algorithm, if you think about the density functional theory, is you need a guess, of course, of the density. From a guess of the density, you generate the Kohn-Sham Hamiltonian. From the Kohn-Sham Hamiltonian, you generate these projected stochastic orbitals by using this Chebyshev expansion. And then you calculate the density this way for one stochastic orbital, and you repeat this multiple times until you're fine with the level of noise that you generated for that specific procedure. And if you do that, you find out something interesting. What I'm showing you here is the CPU time to obtain the energy per electron in, say, a system, say this would be, I think, is bulk silicon or silicon itself, silicon nanocrystals. And so this is the total CPU time to get the energy per electron converged to 10 millielectron volts error as a function of the system size. In this particular case, we didn't go to two large systems. This is about 2,000. This is about 2,000 electrons, and this is about, sorry, this is 2,000 electrons, and this is 4,000 electrons. And what you can see is that the computational effort for the stochastic DFT depends very weakly on the system size. It should, in principle, if we look at this algorithm, and if the Hamiltonian is sparse, which means that if I apply the Hamiltonian and a random vector in my Hilbert space, I can do that with linear scaling. And if the Hamiltonian is sparse and I can apply it with linear scaling, the total algorithm should scale linearly with the system size, as long as the number of stochastic orbitals do not change with the system size for a given accuracy. But it turns out that when we do the calculation, we actually need less and less, this is the inset here, less and less stochastic orbitals as we go to larger and larger systems. And whoever has done Monte Carlo simulations, I'm not sure if this is apparent when you do quantum Monte Carlo, because I've never done beyond a simple drill to teach myself about the method. I haven't played with it, but this is a signature of having self-averaging, and we know that self-averaging can occur if you do a classical simulation of 500 liquid water molecules, and you do the same simulation for 1,000, you need to sample square root of 2 less to calculate observables that are local. compared to when you compare the two systems. And we are seeing the same thing here. As we go to bigger and bigger silicon nanocrystals, despite the fact that this is a semiconductor, and despite the fact that the wave functions, the eigenstates of the Kohn-Sham that we don't calculate, but we know how they look because we do calculate them deterministically when we can, are delocalized across the entire system, we still see a self-averaging behavior by which when we go to larger systems, to converge the energy per electron to the same level of accuracy, we need less and less stochastic orbitals, which is signified here by having a scaling that is better than linear, sublinear scaling for DFT. But what's disappointing in this particular application, which was the first paper we published on this matter, is the total number of stochastic orbitals that we need to describe this system. Now, we would like to work with a total number of stochastic orbitals that is actually much smaller than the number of valence states in your system. Otherwise, you're not going to compete with sparse matrix techniques just because of the prefactor. You have to go to very large systems to see this work much better. And so we don't like the fact that we need to use so many stochastic orbitals, and the remaining work that we've devoted in the context of stochastic DFT is to find ways to reduce the statistical error without increasing the number of stochastic orbitals, but with other tricks. Let me just show you that the fact that the noise is very large actually gives me, in this particular application with 1200 stochastic orbitals and converting the results to the errors that I'm showing you here per particle, so as the system becomes bigger, the the standard deviation per electron decreases, which is what we would expect based on self-averaging. What I want to show you is that this level of accuracy is going to be actually very far from what you need in a DFT application. And the next part of my talk will be devoted to show you how we can reduce that error by about 2 orders of magnitude, which is quite significant, because 2 orders of magnitude means a big reduction in the number of stochastic orbitals. But one other thing that I want to show you before I do that is another place where this approach breaks down. And for example, we wanted to describe the electronic properties of this crystals of buckyballs, and it's a hard calculation because it's quite large. So what happens when we do the calculation stochastically? What I'm showing you here is the density of states for a finite number of stochastic orbitals compared to a converged density of states with a different stochastic sampling. And what you can see is that without doing anything special to the sampling, these are all these dashed lines with different number of stochastic orbitals, and the gap is right around here. This is where the gap between the occupied and unoccupied states is. You can see that with the stochastic approximation, we get quite a big density of states in that gap. Why is that? Because when we have two buckyballs and we describe the total charge of these buckyballs, stochastically, we have fluctuations in the charge. And DFT is so sensitive to those fluctuations in the charge, the total charge, because of the stochastic nature, is not equal to the total number of electrons. On average, it would be, but there are fluctuations. And when you have those fluctuations, this is like charge transfer. DFT is so bad at it, it gives you states in the gap. Those states are going to go away if you add more and more stochastic orbitals. We're going to run out of steam if we don't treat the statistical errors in a better way and just brute force try to reduce the error by increasing the number of stochastic orbitals. Okay, so the first approach that we've used to reduce the statistical errors, and it's necessary, and I'll show you that it's necessary if you want to determine, say, the equilibrium structure of the system and you have noise in the forces, that's going to be a challenge. And so you need to reduce the noise to a level which is small enough so you can use stochastic optimization techniques. So the first approach is to use a reference system, and the idea is quite simple. We write down the total density as a reference density, which we can calculate the density of that reference system exactly deterministically in a linear scaling way. For example, if I have bulk, a chunk of bulk, I work in the field of nanomaterials and I like to study nanocrystals, but I'm not going to give you an example from there. Let's think of a big chunk of a bulk that has, say, many, many unit cells. And the easiest approximation to this would be to chunk the unit cells into, say, to chunk this big supercell into a few unit cells, and each unit cell to calculate the density in each unit cell and to approximate the total density as a sum over the densities of all unit cells. That would be an approximation. Is it a good one? No, it's not a good one, but I'll show you why. But the idea is to have a reference system by which you can calculate its density deterministically quite fast. And an example is to just divide your system into cells. And then the difference between your reference density and your density is just calculated stochastically. And the difference is often small. The better your reference system, the smaller the difference is, and you're going to actually decrease significantly the error if you use that reference system. It turns out that it's not sufficient to divide the system into cells like I just mentioned for a covalently bonded material, by the way. If we think of describing this system using fragments, of course, each C60 would be a fragment by itself, and it would be quite easy. And this is what we've done in the inset, where you see all these three converged results have different stochastic orbitals, and they're all done with a fragment that each C60 is a fragment, and we only correct the difference. And if we impose that, we don't have those charge fluctuations between C60, and it actually works like charm with just a few stochastic orbitals. But for a covalently bonded material, it's really hard to split it in this way, and so we do divide the system into fragments. But to make the algorithm work better, it turns out that because of this projection onto the fragments, the stochastic projection involves a density matrix, the square root of the projection operator. We need also to make sure that not only the density is continuous as you go from one fragment to another, but also the density matrix is. And what we do is we define a fragment with a dress region. We calculate the density in the big fragment plus the dress region, and then only project it onto the fragment, and then build the fragment densities. Each one is this way, and the sum of the fragments gives us a good representation of both the density and the density matrix. And so this is how this works, and I'm just going to focus on the results that I'm showing you down here. But what I'm showing you here, these are quite big calculations. I think we went up to silicon 4,000, so that's 16,000, a little bit more than 16,000 valence electrons. And this is all done on a simple cluster with no communication, internet communication between the nodes, something that I've built 25 years ago when I moved to Tel Aviv. A very simple architecture. And what I'm showing you here are three different results. Two results for different system sizes. The red results are not even the original stochastic DFT that I've shown you before, but those are using silicon 8 as your fragment without dressing it. And in addition, I have used 800 stochastic orbitals, and you can see the level of noise, this is the standard deviation, in the total energy per electron in this system. And you can see that with 800 stochastic orbitals, where I take silicon 8 as my reference system, namely as my fragment, I get quite a large error bar. This would be 10 to the minus 3 electron volts, so this is milli-electron volt, and I get a few milli-electron volts error bars per electron. But if I use a fragment that is 8 silicon atoms only, the fragment itself is 8 silicon atoms, but the dress is 64 or 216 silicon atoms. So I have to do a bigger calculation, but still the fragment is only 8 silicon atoms. I get these blue results, which actually decreased, in this particular case, decreased the error by a factor of 10. And I'm only using 80 stochastic orbitals to do that calculation. So think about it. I can generate the density and the total energy per electrons, and I'll show you forces on the atoms, of silicon with 16,000 electrons with just 80 stochastic orbitals, which is quite remarkable in my view. And there are other things that I don't want to discuss here, but the whole idea is that one way to reduce the noise is to fragment the system in real space, and to use that fragment as a reference system, and then you can play around with a better reference system would always give you a better result. And then this is just the scaling that we find for this particular system. We went very large, and we find, again, as I pointed out, it's whether we do it for one iterations or for multiple iterations. And the multiple iterations, the only difference is, there's no difference, actually. I don't know why it doesn't show the same scaling. But of course, what you can see is what we get a scaling on a log-log plot with a fit that is actually better than linear. And this has to do with linear scaling with B, if I don't have to change the number of stochastic orbitals with the system size. But in this case, to converge the results to a given tolerance, I could have reduced the number of stochastic orbitals, which gave me an approach that is sublinear in scaling. Let me just remind you that we are parallelizing this. Each stochastic orbital runs on a different node, and they don't need any communication whatsoever until the very end, which means that I'm not really saving wall time by taking less stochastic orbitals, but I could use my small cluster computer to do a few calculations, and that's the advantage, of course. The other approach that we've used to reduce the statistical error is based on energy fragmentation. We call that energy window, but the idea is very small. I have to project all my stochastic orbitals onto this occupied space, and it turns out that I can gain an additional computational factor if I, instead of project it onto the entire bunch of, say, if this is my occupied state, if this is my occupied, what we usually do is just project it with a Fermi-Dirac on all the occupied space. But if I can split the occupied space into small spaces, turns out that with one Chebyshev expansion, I can then get the projection on all these spaces together. And because they sample different energy regimes in the occupied space, they become non-correlated, and I can gain an additional savings, or I can reduce the statistical error by doing this. And it actually, there's a limit. If you use one window, you would be back with the original stochastic DFT. And if you use too many windows, they overlap. It means they have a very small, very narrow, and you need a very long Chebyshev expansion to describe them. So there's a balance between the two, using more windows or less. And what I'm showing you here now is an average force on a nuclei. In this particular case, it should be in the equilibrium geometry, so the average force on each nuclei should be 0. And the fact that it's not exactly 0 is because fluctuations, stochastic fluctuations, on average it is. And what I'm comparing is the stochastic DFT, the original formulation, so you can see how big the errors are on representative atoms in the system. So with the stochastic, original stochastic DFT, we get an error of about 1 electron volt per angstrom, which is too large to determine the structure and chemical accuracy of these are the error bars that you have, unless you want to run a very long optimization trajectory, which we don't want to do. And I'm also showing you the energy window with using 10 windows. And here below, I've also used 100 windows. So you can see between 10 and 100, this is summarizing the results. You don't get any gain. But once again, I was able to reduce, just with this energy window approach, the statistical error. Again, I want to say a factor of 10, but I'm going to take a factor of 5 too, which is like a factor of 10. So obviously, the next step, and every time we do that, it takes us about 2 years to get this into a DFT code. It's just so much coding, and it's just the way this thing is structured is a little bit different. But our sort of state-of-the-art situation right now is combining these two approaches together, energy window and fragmentation. So it's not very interesting, the theory itself, but it becomes the density has a very simple form. When you do these combinations, you just have to do a few Chebyshev expansions and you get out the density. But what's interesting is that when you do this, and this is in the upper panel, I'm comparing the energy window with fragmentation to a deterministic calculation of a silicon. This, in this case, is 512, and I'm only showing you the first 50 atoms. And this is silicon with a carbide defect. So I want to show you that it's not just homogeneous systems. There's two carbon atoms that are defect, and they actually put a state in the gap. And stochastically, we have to capture that state to be able to describe the forces properly. And so what you can see when we compare the deterministic to just the fragmentation, this is the green lines, the error bars are quite big. And also there's a bigger bias. You can see that some of the results are often like this one right here. The average is very far away, more than 1 sigma. This could happen, but this is an indication that we also have a small bias in here. So to remove the bias, of course, we would need to increase the number of stochastic orbitals. Whereas when we use both energy window and fragmentation, now the level of noise is actually quite small. It's on the order, I'd say, about 2 factors of 5 from where I was with the simple stochastic DFT. That's a factor of 25, and that's a factor of 500 in number of stochastic orbitals. For the same, a factor of 600 in the computational time for the same accuracy. And so with this level of accuracy now, we can actually go and brute force, use the stochastic forces with the stochastic error to determine the structure. This is not easy, and Ming has been working on this since he moved to Purdue, trying to finish it, so it's going a little bit slowly, but this is the most recent results. I'm just going to show you one main conclusions from this. So this is a training data for us. We take a silicon system where we can use deterministic DFT to do the minimizations. And it turns out that in deterministic DFT, to do the optimizations, we use the method that is called BFGS. It estimates the Hessian by taking the changes in the forces from different times. And it's actually quite an accurate method and converges quite fastly when you're close to the solution, similar like a Newton method. And so it is the state of the art. You can see we've actually compared it to just steepest descent. It's much, much faster than steepest descent if you're close enough to the minimum. And chemical accuracy here would be, you want to be below this bar here, which is 0.01 angstrom per atom deviations. And we've used different methods, but what I want to show you in the take-home message from this plot is with the stochastic level of noise that we have now in the stochastic DFT, where we do both energy window and fragmentation, and with some generalization of this BFDH to be able to work with the stochastic problem, but we've also looked at other methods which are based on a stochastic gradient descent with momentum correction. The point about if you just take stochastic gradient descent, because of the fluctuations in the force, it doesn't necessarily take you in the right direction every step. If you add momentum to it, you have inertia, it allows you to drive a little bit further, and then you average those fluctuations, and you can reach the minimum faster. And this is what we see here. The stochastic gradient descent is the slowest one, and then we have 2 versions of the stochastic gradient descent with momentum. Some of them always go down, some of them do not. But the best approach that we have found is this BFGS, stochastic BFGS. And it turns out that we need to work a little bit harder than deterministic because of the statistical fluctuations if we want to describe the structure at a chemical accuracy. But it's not too bad. And if we want to get much better results, and I can show you, then we just increase the number of stochastic orbitals. There are only 80 stochastic orbitals here. And if we do 320 stochastic orbitals and the error bars go by a factor of 2, we get a significant improvement in how fast we converge to the chemical accuracy. That's the deterministic result. Well, no, this will converge eventually. I stopped running it here, but you have to look, this is where you would stop running it if you wanted chemical accuracy. We just let it go for more. Okay, there are other aspects of this, but I'm not going to go into them. I think I have about 10 more minutes. Is that so? 15 minutes. Total, including, I thought I had 50 minutes plus 10 minutes discussion, right? And we started, total, okay. So that gives me, you're saying 15 minutes total. So let me just say that we've also tested how this thing depends on the system size, because it turns out that when you do something for one system and you try to do it for a bigger system, things often change. And you have to make sure that the conclusions you reach for a smaller system also hold for a bigger system. So we study this as a function of the system size. And we also studied something that is, we started from the perfect structure of the deterministic DFT, and we let the stochastic algorithm go. It's going to move away from that structure because of the fluctuations, and this is what I'm showing you here on the right-hand side. And what you can see is that this is a test that we want to make sure that as we go to a bigger system, we're not going to introduce, the accuracy is not going to go down. It turns out that in this particular case, the accuracy actually improves. If I started the perfect structure and I let a silicon 512 move, it actually moves on average about 0.004 angstroms away from its perfect structure, whereas a smaller system moves further out. And that has to do with the fact that we kept the same number of stochastic orbitals. So because of self-averaging, there's less noise in the 512, so we can do a little bit better. And then we can study how things behave with the noise and so forth. But I actually want to move, because I only have 10 minutes, to the last part of my talk, which has to do with an application to warm dense matter. So the main idea behind doing stochastic DFT is to be able to determine the structure, if you can determine it in any other way, and to get the ground state density of the system, because that's an input that we would need to describe excited states. If we do a GW calculation or a beta salpeter, which is what we do post DFT, then we need that density. The other place where stochastic DFT has an advantage is to describe warm dense matter, and that has to do with the fact that in warm dense matter, you're taking your system to elevated temperatures, which are about this high, 10,000 Kelvin. And at those temperatures, think about a deterministic DFT calculation. You basically have to find all the eigenstates, because the population of all states at that temperature has a finite population, which means that if I have a matrix that is that represents a silicon 512, and the basis set that we use for that could be, we use about 0.5 atomic units, so it could be 100 by 100 by 100, a million basis set for just silicon 512. I cannot find all the eigenstates, even with a sparse solver of that system. So it's challenging, and so people make truncations, and they don't go to high enough temperatures as in the experiment. But it turns out that the stochastic DFT has a natural advantage in describing, and it's true also for TD-DFT, a natural advantage in describing warm dense matter, and that's what I'm going to show you now. So I'm going to show you two examples. First, to understand what stochastic DFT, how to use it at a finite temperature calculation. And then I'm going to show you the equation of states for mixtures of helium and hydrogen, which is an interesting system, experimentally interesting system. And so once again, finite temperature stochastic DFT, the only place where we have to change anything, and we don't have to do anything, is actually we have to put temperature in our projection operator, and we have to include, if we want, the entropy in the free energy, if we want to calculate free energies. If we want to calculate the energy, we don't. In any event, for a semiconductor that I've shown you before, we also have to put a temperature, and numerically we can never study a step function. So what temperature do we put for silicon? And why did I take silicon as an example before? I took silicon because silicon has the smallest band gap that I know from DFT. There are materials with smaller band gap, but it has a very small band gap in DFT LDA, which is the applications we did. The band gap is 0.6 eV. The smaller the band gap, the harder we have to work to project onto the occupied space. In other words, the longer the Chebyshev expansion projection is. Now, for silicon with a gap of 0.6, we had to take a temperature to filter the occupied from the unoccupied states, which was about 600 degrees Kelvin. So just twice the room temperature. We've done an application for a metal. We just put the room temperature for a metal, and that just gives us Chebyshev expansion coefficients that are twice as long as silicon. So it's doable. But here, when we want to put high temperature in, we just change the projection, and then we don't only project onto the occupied space, but we also project with a certain probability onto unoccupied space. But the nice thing is that as we go to higher and higher temperatures, the length of a Chebyshev expansion becomes shorter and shorter. So in stochastic DFT, we actually have to work less and less hard. This is wall time to the calculation for silicon-64 with some fragments and only 80 stochastic orbital versus a deterministic calculation. And I want to converge. This is converging the calculation to describe whatever, the free energy of this system. Deterministic DFT, as you increase temperature, you need more and more states. That's an n-cube operation or a t-cubed operation. So in deterministic DFT, this is the scaling that you would expect with the temperature. But in stochastic DFT, it scales almost linearly with the system size. But as you go to higher temperatures, you need shorter and shorter Chebyshev expansions, and this is what you see here. And so naturally, this is an advantage, of course. And then finally, this is the scaling with the system size for this case, of course, showing that I'm not showing you the scaling itself, but it is sublinear here compared to the cubic scaling of deterministic DFT. So what else we can do with this approach? We can calculate, for example, and this is, I'm not sure why that community, maybe you would know, uses DFT to calculate transport properties. You shouldn't. You should use TD-DFT. But that's what they do. So we did the same and calculated transport properties, coefficients. And in two cases, in situations where you have an insulating phase, and this is, you can learn about this insulating phase by not having any conductivity at zero frequency, or a metallic phase by having a finite conductivity at zero frequency, and these are the error bars that you can see from the stochastic DFT calculations. And then you can devise a sort of like a phase diagram by which you ask yourself at what fraction of hydrogen you would have a transition from a metallic to an insulating phase, and you can delineate the behavior using stochastic DFT, and you cannot do that with deterministic DFT. It's just too expensive. And so with that, I'm going to stop because Chion wants to kill me already. Thank you.